So now I'm recording.
What was the answer again? Sorry.
The answer was 18.23 angle 63.4. Okay, so I will skip the next one, although I'll do a video for it. Choose the load impedance. Actually, I think this one's real. Let me see how quick this one is. Shouldn't be that hard. I'll tell you what to do, and then I'll make a video for it later. So the way to find where the power dissipated is a maximum, what you want is for your load impedance to have an imaginary part that cancels out the imaginary part of the source. So what you want to do is you find the Thevenin equivalent of the source. It's the wrong pen. So you find the Thevenin equivalent of the source, and you find its impedance. And if you do that correctly, I believe you get 0.8 minus J 2.4 ohms. And then for maximum power transfer, you want your load impedance to be the conjugate of your source impedance. And so you would want your load impedance to be 0.8 plus J 0.24 ohms. And then, so that would tell you what your load impedance ought to be. And then to figure out what the maximum power is, the maximum average power is, and I don't know if this formula is on the sheet or not, but it's 1/8 times the magnitude of the source voltage squared over the resistance of the load impedance. To get the voltage of the source, that's going to be the same as the voltage of the open circuit that you got when you found your Thevenin equivalent. And your average maximum power should come out to be 12.5 watts. But I'll make a video on this tonight or tomorrow, because your test is Wednesday, right? At what time is your class? 11:30. Okay. All right. I probably have in me enough to do. Oh, I should do 14. Okay, I'll do 2 more. So I'll do 14, and then y'all can be looking ahead to decide if you want me to do 15 or 16. Just so you know, I did one similar to 16 already that's recorded. And 15. Actually, they're very similar. So 15 and 16 are similar, and I've done one like this, but I'll do 14 now. Okay. Oh, and I don't think I have the answer to this one. So this is since I don't have the answer, it's good. I can get whatever I want, and it'll be correct. All right. So in the network below, the load consumes 9.2 kilowatts at a power factor of 0.80 lagging. By adding a shunt capacitor C, the power factor is improved to 0.85 lagging. Determine the value of C. So this mess over here is just saying that my impedance has, or my inductor has a value of J omega 30. Is what that's saying over there. So we know from those formulas that I put on the front that the value of our shunt capacitor is going to be Q old minus Q new over omega v RMS squared. Oh, not only do I not have the answer, I made this problem up, so we couldn't end up with something completely ridiculous, like, you know, a negative resistance or something. Who knows? Okay, so let's see. Omega, how do we find omega? 2 pi times the frequency, and our frequency is 60, so 2 pi times 60, and that is 376.9. And let's see. So our Q old is 9200, power factor 0.80, and we know that our new power factor has to be 0.80, so we'll have let's see. Let me get first my voltage over the load. So the voltage for the load is going to be our total voltage. So I'm doing voltage division times j omega 30 plus 50 over j omega 30 plus 75, which is 1000 times j times 376.9 times 30 plus 50 over j times 376.9 times 30 plus 75, and I'm going to let somebody tell me what that is. Somebody is doing it, right?
Yeah.
Okay. I get 1,000.
Yeah.
Plus,
1,000.
and I made the problem up. How does that happen? Plus J 2.2.
Yeah.
Oh, I know how it happened. Yeah, because this is, yeah, that's almost 1. J 2.2. And yeah, I did a bad problem. Yeah, 1,000 angle 0.126. Yeah, that's what I get. 1,000 angle 0.126. Yeah, so this is not the best problem. Okay, but then when you add the shunt capacitor, the real power doesn't change. And so the 9.2 kilowatts, that power is going to stay the same. And so when we have our new power factor, we know that Q equals the power factor times the tangent of phi, or the power factor times the tangent of the inverse cosine. That's not the power factor, the real power. So P is the real power times the tangent of the inverse cosine of the power factor, which is 0.80. And so the real power, which doesn't change, is 9,200 times the tangent of the inverse cosine of 0.8. Now I was changing it to 0.85. That's going to be our new power factor, 0.85. So I'm trying to get our new Q. And so it'll be 9,200 times the tangent of the inverse cosine of 0.85, which is 5701. So our new Q is 5701. So our old Q, I said, was 9,200, but that was not correct. Yeah, old Q should not have been 9,200. Our old Q should have been 9,200 tangent inverse cosine of 0.8, which is 6,900. And so our Q old minus Q new over omega V RMS squared will be 6,900 minus 5701 over omega, which was 376.9 times V RMS squared, which will be 1,000 squared, which is 3.18 microfarads.